Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. The series we're in is Individual and Social Choice. This is the 9th installment in the series. Last time I started the setup of Arrow's theorem, I actually didn't get to it. So we're going to continue our axiomatic analysis of voting rules. The main goal of this will be to state and prove Arrow's theorem. So this will be Arrow's theorem continued. So we've defined the idea of a general social preference function, and so that was a mapping. It was defined on the set of all preference profiles. Just denote that by this blob here. And to each preference profile, it assigns an asymmetric relation on X. So that's this blob here, okay? So once we had that idea, we could define axioms for general social preference functions, and we looked at 3. The axioms that we looked at last time were rationality. The social preference function always generates a ranking. Independence of irrelevant alternatives. The social preference between any 2 alternatives only depends on individual preferences between those 2 and doesn't use any information about preferences over alternatives other than those 2. In other words, you can think of it as just a pairwise vote where you have individuals raise their hand if they prefer X, other individuals raise their hand if they prefer Y, and that gives you all the information you need to figure out if X beats Y, or the reverse, or neither. And the last axiom was Pareto, which just means if every individual prefers one alternative to another, then the social preference function respects that preference, and the first will be socially preferred to the second. Well, all right, so what we're going to do is we're going to impose these 3 axioms. We're going to say, okay, we're only considering social preference functions, satisfying them. What does that leave us? Okay, that's the whole point of Arrow's theorem. And one way of thinking about this is as follows. So this blob that I just drew, I want you to think of that as all social preference functions. Right, so it's a set, it's a big set. Majority rule is in there, Borda is in there, any other voting rule that just relies on individual rankings to compute social preferences is in there, okay? Now, what I'm going to do is I'm going to sort of do a Venn diagram version of the statement of Arrow, and then we'll actually give a formal statement. So in this space of all social preference functions, I can look at the social preference functions that satisfy rationality, for example, okay? And that's going to be a blob. Right, so that is all the social preference functions satisfying the rationality axiom. Let's do one for IAA. Okay, so here's a blob consisting of all the social preference functions satisfying rationality. And then here's another one for Pareto. But anyway, so each one of these blobs you can think of as isolating the social preference function satisfying the corresponding axiom. And we've talked about a couple, right? So we talked about majority rule, which satisfies IAA. It does satisfy Pareto. Okay, but it doesn't satisfy rationality, so it's outside that rationality blob. So here's majority rule. Borda satisfies rationality and Pareto, but not IAA, so Borda will be over here. Okay. What we want to do is find the social preference functions that satisfy all three axioms at the same time. So we want to find, that is, we want to understand what are the social preference functions in this intersection of all three of the blobs. Okay, that's what Arrow's theorem tells us. It tells us which social preference functions are in there. So the what we're going to find is, if you just impose one or two of the axioms, there's plenty of social preference functions that satisfy them. But when you impose all three axioms at the same time, you're left with very few, and they're not normatively interesting or justifiable. And I should say this is often what happens with axioms, that when you look at them separately, they seem reasonable, weak, but sometimes when you combine them, they have unexpected joint implications. The joint implication of all three of these axioms is that the social preference function is dictatorial. So what I mean by that is that there's one individual, and whenever they prefer one alternative to another, then so does the social preference. Okay, so that individual imposes their strict preferences on the rest of society. That is a very extreme kind of social preference function. It concentrates all power into a single individual, essentially. And obviously, those are not very interesting. We wouldn't want to say that that's desirable for society. But it turns out that the only social preference functions that satisfy all three of the axioms are dictatorial. Okay, and that is a pretty surprising implication to get by combining these three reasonable looking axioms. And Arrow's theorem at the time was revolutionary, and it's still it's still taught. It's still really sort of at the core of social choice theory, and actually a lot of the literature has over the last decades has been in response to Arrow, either generalizing Arrow or trying to find different ways of formulating the problem. So let's go ahead and state the theorem. So when stating a theorem, sometimes we'll have to define some terms here, and we just used one that we have to define, dictatorial, right? So what does that mean? Well, social preference function F is dictatorial if there's some individual let's call that person I, such that the following holds. For every profile and every pair of alternatives, if that individual prefers X to Y, then so does society according to the social preference function. Okay, so I mean the impact of this is that it's the same individual for all profiles. So even if everyone else in society has the opposite preference from this guy gets his way. Okay, so the idea of a dictatorial social preference function, it's very extreme. It's not very palatable. Nevertheless, here's Arrow's theorem. All right, so I haven't said it explicitly yet, but we're going to assume the set of alternatives contains at least 3 elements. So there are at least 3 alternatives. All right. If the social preference function satisfies the 3 axioms, so that's rationality, IIA, and Pareto, then it's dictatorial. So the only way to satisfy all 3 of those axioms at the same time is to concentrate really almost all power into a single individual. Okay. I've been a little bit imprecise about what the domain is here, I should say. I'm saying all possible preference profiles. You can formulate the theorem in different ways. Sometimes people will simplify things and assume that individuals can't have any indifferences. So in their rankings, there's no 2 alternatives ranked at the same level. But for what we're doing, we can just let individuals have any ranking, any weak orders. There's a little bit of wiggle room here. Suppose the dictator is indifferent between 2 alternatives, then the social preference isn't pinned down. So that's why I'm saying the dictator has almost all power, but essentially the dictator does have all power, because whenever they have a strict preference, then so does society has the same one. So that's the theorem. And the rest of this installment, I just want to go through the proof of this. There's going to be a little bit of setup in the proof. I want to introduce some shorthand notation and some concepts that we're going to use. But I'm going to use a proof of Arrow that is, I think, less involved or complicated than a lot of proofs I've seen. So let's just jump into the proof. This will be, heavy lifting. So if it's the first time you've seen it, you should probably expect to be confused, and then, look at it again a couple times, and everything should start to fall into place. All right, so let's begin with some setup here. All right, so what we're going to do is, this is basically a big conditional statement, okay? We're going to begin with a social preference function. Let me just say SPF. And we'll use the usual notation, little f. We need to show that if it satisfies the 3 axioms, then it's dictatorial. So that's a conditional statement. So we're going to suppose the antecedent. We'll suppose that f satisfies the 3 axioms. And then we need to show there's a dictator. Okay, I'll talk about the sort of the overview of the proof in a minute, but first let me define some terms. Let me denote profiles just to save some writing. Instead of writing out P1, P2 to Pn, let me just use a capital P for a profile. Or if I have a different profile, I might put primes on it. And instead of writing out the list, I'll call it P prime. I might have double primes. Right, but I'll just use one P to denote a whole profile. Now, when we talked about individual preferences, we started with a strict preference relation, and just like we did then, we now have for any profile P, the social preference function gives us a strict social preference. And I'm going to just use this P notation now. When we talked about individuals, though, we then talked about, we defined weak preference, okay? And we can do the same thing here. We can define the weak preference relation that corresponds to the social preference. I'm going to use this notation R again, and I'll put a little F subscript so we know, just so we know that it's being generated by the social preference function that we have here. So the weak social preference relation is defined as follows. I'm just going to use the same convention as we did for individuals, okay? For any pair of alternatives, we'll say that X is weakly socially preferred to Y if and only if it's not the case that Y is socially preferred to X. I forgot the not. Okay. So that's just the same convention that we used and remember, we're assuming here that F satisfies rationality, and so this strict social preference, it's a weak order, it's asymmetric and negatively transitive, okay? And therefore, we can think of it as a ranking. And, if we write, if we have X socially preferred to Y, that means X is higher than Y in the social ranking. And if we write X weakly preferred to Y, that means in the social ranking, it's ranked at least as high as Y, okay? Could be at the same level or higher. Okay. So, so now that we have the social preference function, we're going to be talking about groups of individuals, okay? And I want to define a property of groups. Okay, so given a group of individuals, I'm going to use a G to denote groups of individuals. And if you remember this set inclusion notation, this is just saying that the group is composed of individuals, right? So given a group and given alternatives X and Y, we're going to say that G is decisive for x over y if the following holds. Okay, the group is decisive for x over y if for every preference profile where the members of G prefer x to y, then the social preference is also x preferred to y. Okay, so formally it's just basically writing that out. Actually, I'll use our shorthand. So for all profiles P, if everyone in the group prefers x to y, then x is socially preferred to y. Okay, so that's decisive for one alternative over another. So a decisive group has some power. I should say, if a group is decisive for x over y, that means it has some power. It's specific to those two alternatives. It just means that when all members of the group prefer x to y, society also has to have that preference. Okay. In this case, we're going to write, use this notation, x d g y. All right. So this dg thing here, this you can think of as the decisiveness relation for the group, for G. Okay. Right. It's just it's a binary relation, and it just it's basically a list that tells us which alternatives or which pairs of alternatives the group is decisive for. Okay. Technically it would be ordered pairs of alternatives, but fine. All right. So if you have one group, it might be decisive for some alternatives over some others, but not for some different ones over some others. This decisiveness relation just tells us which xy pairs are such that the group is decisive for x over y. So and okay, let me give an example of this. So for majority rule, for example, if we have two alternatives, x and y, and we have a group of individuals, we can ask, okay, is the group decisive for x over y or not? Well, imagine a preference profile, and we put the members of G over here, let's say, and everyone outside G is to the right. Suppose we have a preference profile where everyone in G prefers x to y. Well, G is decisive for x over y if that implies that x is majority preferred to y, right? For G to be decisive for x over y, it must be that when they have that common preference for x over y, then the social preference must also be x over y. For majority rule, this is actually a pretty, it boils down to a simple idea here. Suppose G has more than half of all the individuals. That means G is a majority. So if everyone in G prefers x to y, then no matter what the preferences of these other guys are, x will be majority preferred to y. So if G contains more than half of all the individuals, then yeah, X, it will be decisive for X over Y. Okay. But suppose that G has not a majority. So suppose it has less than or equal to n over 2 individuals. Okay. Now it's not going to be decisive, and here's why. Because I could pick a profile where everyone in G prefers X to Y, but everyone outside G prefers Y to X. Okay? So remember, for majority rule, X beats Y if there's more people who prefer X than prefer Y. But if G is not a majority, if it's less than or equal to half of all the individuals, for this profile, it is not true that the number of people who prefer X is bigger than the number of people who prefer Y. For this profile, in fact, for this profile, we would have Y being weakly socially preferred to X. Okay, X would not beat Y. And that means that it is not the case that this group is decisive for X over Y. Okay, so, all right, so in fact, so for majority rule, you know, if the group is big enough, it'll be decisive for X over Y. But if it's too small, it won't be. Now you can imagine though, there are different, you know, we want to be very general here and allow for social preference functions that give different groups of people different power over different alternatives. And, you know, you can imagine a social preference function that gives very small groups special power to decide between different, you know, pairs of alternatives. For majority rule, it's simpler. So that's the idea of decisive for X over Y. Okay, now what we just talked about is it's an authority of a group that's specific to a pair of alternatives. All right, let's just build on that a little bit more and say a group G is decisive with no qualifiers about alternatives. We'll just say it's decisive if for all X and Y, G is decisive for X over Y. And then, of course, we could just write that as like so. Okay, so this is, so a decisive group is just a group that has this authority between all pairs of alternatives, okay? Going back to majority rule, if a group has more than half of all the individuals, it's going to be decisive for any X over any Y, so it's actually decisive. Let me just nail this down a little bit more. Go back to the majority rule example just so so things are really crystal clear. Let's look at, let's keep things manageable and just think about three individuals, three alternatives. And with three individuals, there are, well, there are 2 to the third groups. Okay. What are those? Well, we have 1 by herself, 2 by herself, 3 by himself, 1 and 2 together, 1 and 3 together, 2 and 3 together. We could have everyone together. And then there's a last group that doesn't have anyone in it. Okay. So there are 8 different groups. And I just defined this decisiveness relation for each group. And so we can actually do that for each of these groups. Okay. So let's first take the decisiveness relation for a group, and let's first think about the group consisting of 1 and 2. All right, and this relation we can graph. And like we said, right, if a group has more than half of the individuals, then it's going to be decisive for any alternative over any other. So the decisiveness relation for this group is like so, all right? The group of 1 and 2, if they prefer A to B, then no matter what the other guy thinks, A is going to beat B in a majority vote. So I'm drawing this arrow, this arc from A to B, right? As well, if both 1 and 2 prefer B to A, then A beats, sorry. If 1 and 2 both prefer B to A, then B is going to beat A. So I'm going to draw an arc going the opposite way. Okay, and that's true for all of these pairs. Okay. In fact, the decisiveness relation looks the same for any of these groups that consist of a majority. So if the group is 1 and 3, or actually I'm not writing this very well. Okay, I'll use a comma here between these. So if the group is 1 and 2, or 1 and 3, or 2 and 3, or 1, 2, and 3, the decisiveness relation looks like this. There's arcs going between every pair of alternatives. I'm not going to worry about these. They're vacuously there. Let's just not worry about that. So that means these groups are decisive. Okay. What if we look at the groups that don't contain a majority? So 1 by herself, or 2 by herself, or 3, or just no one. Well, if we were going to do the decisiveness relation in that case, there's basically no arcs because, again, if you take, for example, A and B, if person 1 prefers A to B, but everyone else is opposed to her, then, you know, A does not beat B. So there's really no arcs here unless you want to put these sort of trivial arcs. But again, that's just a technicality. So, so that's the idea of the decisiveness relation. This is for majority rule, I should say. Write that down. For a different social preference function, these graphs are going to look different. Okay. So, all right. I think that's all the setup we need. And we can start getting into the proof. I see that this has gone long, so we're just going to take the proof into the next installment. So I'll stop here and I'll see you in the next one.